As Lee mentioned, this is the post-lunch talk on the second day, which means it is the talk meant to be the most lighthearted and humorous, which is perfect for me because I am, of course, a humorous person. Okay, that's all the longer I can keep that up. I'm actually really happy to be here, specifically speaking at DevOpsDays Dallas, because I'm in the process of moving to Dallas. Yeah, thanks. I'm almost 3 months in at a new gig at Sabre, and they've graciously given me the time to come out here and speak to you. So I'm going to talk about uncoupling, which you might infer is the reverse of coupling. Just a little bit about myself. I am a developer, an architect, an author, and I've also lived in operations. And in fact, I was living in operations at a time when most developers never really thought about what production was. They usually didn't know what their hardware was. They didn't know what their network environment would be. You didn't know about firewalls existing until you were on the verge of release and suddenly had to cough up a list of port numbers that needed to be opened. It was really kind of a different era. And here I was, responsible for the availability of a system that I didn't write, but I got woken up at 3 in the morning whenever it would fail. Fortunately, I started to find that the failures came in patterns. That gave me hope, because if every failure were unique, then it would be an endless treadmill of 3 a.m. calls. But if they come in patterns, maybe we can find patterns to solve them. That was the genesis of the book, Release It. I'm delighted to say that it's been embraced by the developers that I targeted at. And it is now in its second edition because a few things changed over the last 10 years or so. So let's talk about systems that you've been working on for some time. You've been in it for a year, maybe 2 years. Things are going nicely. You've found some elegant symmetries. You've found ways to factor it into small components. We probably say that they're loosely coupled. We think that they're loosely coupled anyway. We think that the pieces are orthogonal to each other. But then the fateful day comes, and somebody asks for a requirement that isn't one more of something you've contemplated before, but it's something completely different. Maybe it's now something that was a one-to-one relationship needs to be one-to-many. Or worse yet, 2 different entities need to be carved up, half of them glommed together and becoming a new entity. And you start to make changes to your system. You refactor it to make the change easy, and you keep working and you keep working, and somehow things are getting worse and worse, and you realize what you have is not that beautiful structure of buckyballs, but you have something more like a tensegrity structure. This was Buckminster Fuller's idea about architecture, where you would have rigid beams being held together by springy ropes. And so the combination of tension on the ropes and the integrity of the beams would allow you to hold a structure up. Now, tensegrity structures are interesting because they seem to sort of float in midair until you remove the wrong beam and the entire thing falls down at once. So having a tensegrity structure maybe isn't exactly what you were aiming for. You continue to refactor, you continue to pull on strings and ropes and move beams, and soon you realize you do not have the crystalline array of buckyballs from the beginning. What you have is more like a magnetic putty that's engulfing everything as it goes. You don't have integrity, you don't have tensegrity, you have no-tegrity. The system seems like it's fighting back against you. You had a change that you estimated was only 2 weeks of work, because pretty much everything is just a couple of weeks, right? But now you've fallen prey to the coupling, and you realize all these things were coupled together, and it's a little bit like when you reach that page in a Choose Your Own Adventure book that says, "You have died, go to page 1." Well, this is why we have version control. Git is like keeping your thumb in the page of the Choose Your Own Adventure book. You just revert back to the last page when you were still alive, and you try a different pathway. Well, what is this coupling? We all have kind of a visceral feeling for it or an intuitive sense, But I've spent a lot of time trying to understand coupling in various forms and guises. And one of the things I found interesting is that in other industries, coupling is not a dirty word. In fact, coupling and couplers are essential in other areas. This, for example, is a Scharfenberg coupler. It was invented more than 100 years ago. It exists to hold two train cars together. Inside of the cone-shaped indent, we have a very clever arrangement where a rod comes in, pushes a wheel around, and eventually something on a big spring locks into a little semicircular gap in the wheel, and it now holds together and will not come apart unless you insert a mechanical key and apply force to get the whole thing to come apart. This Scharfenberg coupler also helps you maintain pneumatic and electrical connections between train cars. This is one of the reasons that trains coming apart is not nearly as much of a problem as Saturday morning cartoons led me to believe. Well, that and quicksand. Turns out quicksand is not around every corner, and trains don't randomly drop off cars. Although, fun fact, in researching this talk, I found out that in England, for a period of time, they actually had trains that would get shorter as they went. So instead of stopping at a station, they would just unhook the last couple of cars and let them drift to a halt somewhere near the town you were trying to leave them at. Well, sticking with mechanical engineering, here is something called Watt's linkage. This was invented by the famed Scottish engineer James Watt. And you can see that this is an assemblage of three beams, two fixed couplers, and two movable couplers. Now the purpose here is to turn rotary motion into linear motion. This was a huge invention, and it allowed a steam engine to drive a giant beam pumping water out of wells so you could dig up more coal to run the steam engines, to pump water out of the wells to dig up more coal to run the steam engines. Well, this was so famous that Watt got a patent on it. And at that time, patents were not an industrial system. I think his patent was number 3 in England or something like that, hand-signed by the Queen. Today, this is still celebrated on the Festival of James Watt in Scotland, where they parade through town with banners bearing this emblem on it. Well, all right, I made up the last part, but he really did get a patent, and it was in the single digits. Now notice that this is a very simple construct. Just a few pieces, quite general in their movements. Well, here we have something called Chebyshev's linkage. Also, 3 beams, 2 fixed couplers, 2 movable couplers. And this one turns out to provide a better approximation of linear motion from rotary motion, but it's the same parts, just arranged a little bit differently. And in mechanical engineering, having different parts, same parts arranged differently can give you very different outputs. When we deal with coupling in our arena, if we try to arrange the same parts differently, it generally just doesn't work at all. It's not that it gives you a better approximation or a worse approximation of linear motion, it's no motion. Let's move away from mechanical engineering to one of my favorite subjects, quantum mechanics. I know you're all ready for quantum mechanics right after lunch. I promise it won't hurt too much. Physicists have something called the Standard Model. The Standard Model describes the fundamental particles of the universe. This is at a level much smaller than electrons, protons, and neutrons. Well, electrons are in there, but protons and neutrons are a derivation from this model. In this model, where there's a line between 2 particles, it means that there is a coupling coefficient that describes how the field of one particle interacts with the field of the other particle. Wherever there's not a line, it means that the particles don't interact. This model is why we are all here. Quite literally. Without this model, without the coupling in this model, there would be no matter. So coupling is pretty important to me in this area. When we think about coupling, in the mechanical sense, when we think about coupling in physics, what we see is it determines the degrees of freedom of a system. So if you think about those couplers in Watt's linkage, they allow the system to move in a two-dimensional plane. And it allows the system to move such that the pin in the middle transcribes this line back and forth. That inherently means that it allows some movements and prohibits others. A closer example to home would be your knee. Your knee allows your leg to move in roughly one plane of motion, but it inhibits motion in the perpendicular direction. Technically, yes, you can move your leg in the perpendicular direction, but generally just once. The other thing that coupling does is it connects effects that otherwise might be quite distant and independent. And this is where we start to get into some trouble. I'd like to give you an illustration of these connected effects. This is Iapetus. It's one of Saturn's moons. It's sometimes called the Death Star moon for this rather striking crater feature that we see on the right-hand side of the image. But there's another interesting thing about it, which you can see in the left-hand side of this image, which is this dramatic two-tone coloration. This is not an, this is not an artifact of the telescopes used to capture this. This is actually how the moon looks. Well, this was observed originally by Giovanni Cassini, for whom the Cassini gap is named. He drew the rings. The Cassini spacecraft is named after him. But Giovanni Cassini was roughly a contemporary of Galileo. So we know that this has been around for some time. Sorry, our knowledge of this has been around for some time. But we didn't really understand why until 2009. In 2009, we discovered the likely cause of this two-tone coloration, which is this. This is Phoebe. It is also one of Saturn's moons, a particularly small one. In fact, astronomers sort of sneer at moons this small. They're like, look at this pathetic thing. It can't even pull itself into a sphere. Because it's so small, it's got very weak gravity. It's only about 213 kilometers across. I think that actually means it takes longer to drive across Dallas than from end to end on this moon. It's small enough that when it's hit by micrometeorites, particles are ejected, bits of dust and rock and grain, and they form this ring. This is a ring that was also unknown until around 2009, when we discovered it as the largest of Saturn's rings. Well, in fact, it's so large that you can see all of Saturn's previously discovered ring system is just the tiny inset in the middle of the picture. It's also so diffuse that you can't see it from Earth. It appears to be made up of material from Phoebe. In fact, Phoebe orbits at the outer edge of that ring. The dust and rock that's ejected from Phoebe orbits Saturn for millions of years until solar pressure and tidal forces from Saturn cause it to spiral inward to the inner edge of that ring, which, you may be ahead of me on this one, the inner edge of this ring is where Iapetus orbits, sweeping up the debris that was blown off of Phoebe millions of years ago. I think this is a particularly beautiful example of coupling. We have sunlight, gravity, this beautiful diffuse ring, millions of years of time, creating a rather dramatic effect on Iapetus. So I say everything is coupled to everything. Your systems have ambient temperature. Programmers tend not to worry about the ambient temperature. Data center operators do worry about it. There's ambient atmosphere. We don't often think about the fact that our systems run in an atmosphere and are subject to atmospheric pressure. But when you put a system out in space, suddenly this matters, and you can get things like metal migration, growing whiskers in your chips. We don't think about acoustic vibrations, but there's a pretty dramatic video of a guy screaming at his hard drives, and you can see the latency goes up. That's pretty interesting. I wouldn't have thought that yelling at a disk drive would affect it. I mean, a potted plant maybe, but not a disk drive. We run all of our systems in a gravity well. I haven't yet figured out how that one can be broken, but there's all these forces that we don't always think about. And that's probably for the best, because if we tried to think about everything all the time, we'd never get anywhere. So there are some kinds of things we worry about more, and some we worry about less. When we talk about coupling, there are kinds of coupling that are on my mind more and less. So for example, we can have operational coupling. This is what would get me up at 3 in the morning. Operational coupling means one system can't run without the other one running. Anyone who's doing synchronous HTTP-style interactions, you have operational coupling. We also have development coupling. This is when the producer and consumer have to change in a coordinated way. Over time, we've been discovering better ways of reducing the development coupling, but it still crops up once in a while. One of the original microservice architects had a rule that said you can only ever deploy one microservice at a time. You're not ever allowed to deploy 2 of them together in the same deployment. And that was a pragmatic approach to try and reduce the development coupling. A very sinister one is this semantic coupling. This is when there's no obvious connection between 2 things, but if you change the representation of a concept in one area, it necessarily requires a change in another area. These are the kinds of things that we hold in our heads. We don't often write them down. And when somebody asks, how hard is it going to be to implement this feature, we start to reel off all the places where the semantic change ripples through systems. And let me tell you, if you're on the receiving end of that kind of communication, it can be quite frustrating. Functional coupling is kind of the inverse of semantic coupling. So in semantic coupling, there's no direct call or direct interaction, but we still have to change together. Functional coupling says we have to change together because the systems do similar things. And if we change the definition of what it means to do similar things, we have to change both of them. A great example is anything that deals with credit card information underwent a change where all of a sudden they all had to be subjected to PCI restrictions and walled off from the rest of your world, like, it's plutonium that's going to infect everything and irradiate the rest of your world. And then, of course, there's incidental coupling, where there's just no good reason for these 2 things to be coupled, but one day you discover that your e-commerce site won't start up if the MQ broker's down, and no one can quite figure out why. I want to get a little practice using these ideas and look at one interface that we can build several different ways. So here's an interface that says we send notification that a report is ready to view, and it's just going from an email component inside of an application, talking to an external email system, in this case, Microsoft Exchange. What kind of coupling do we have here? Well, we certainly have operational coupling, right? If Exchange is not there, then you can't send the email, the function doesn't work. SMTP itself is not very robust against interruptions, and so even if you have a changeover of IP address or a failover of the node or a short interruption, you have to restart the conversation. So we definitely have operational coupling. The development coupling here, I would say, is weak. Technically, you would have to change your implementation if for some reason SMTP itself changes. That doesn't happen very often. Usually there's a long lead time, it's a well-understood protocol, there's pretty good interoperability. So I'm not too worried about having to redeploy my email component when Microsoft Exchange changes. The semantic coupling here is quite strong. Both sides must know about the idea of envelopes, recipients, message bodies. They have to understand the right way to format the headers of the message, the body of the message, and even the ending of the message. The functional coupling, on the other hand, is quite weak because the responsibilities of the 2 sides are very different. On the Exchange side, you're managing disk queues, you're managing space, you're dealing with a lot of connections to external systems, you're managing identities, you're applying spam checking rules, these sorts of things. On the email sending side, you're really just worried about a report. You get an event that a report is ready, you send a message. So there's not a lot of shared responsibility that would cause us to change them both at the same time. Maybe we look at this, though, and we say, all right, that operational coupling looks pretty strong. I'd like to weaken that. We don't like synchronous, conversational, request-response protocols. So what can we do to reduce the operational coupling? Well, we could take another approach. Moving on to a different example, but same ideas. In this case, we've got our SQL connection going to our reference data system, which is presumably a database, and we have some coupling here. Operationally very strong, similar to the email case. If your database is not there, you can't make a database query. The development coupling is pretty strong because we have a schema on one side that's known to the other side, so the likelihood of having to change both sides of this connection at the same time due to development changes is pretty high. The semantic coupling is very strong as well. We have tables, columns, joins. Both sides need to know about it. They both have to embed the same abstractions. But the functional coupling is weak. Even though they're embedding the same abstractions, their responsibilities are quite different, and so we're probably not going to have to change both sides at the same time because of a functional change. All right, now we're looking at the operational coupling and saying, let us reduce that. So let's say maybe we're going to use a REST call instead of SQL to try to reduce the strength of that coupling. Well, our operational coupling is strong but less strong than before. SQL is a connection-oriented protocol. It stays alive for a long time. An interruption means you have to rebuild a connection. HTTP, not so much, right? It's kind of one and done, one and done. The development coupling is still strong, but somewhat less so, because now in the REST component on the left-hand side, we have the ability to implement multiple interfaces. And so we can insulate the right-hand side from changes to a degree. The semantic coupling is still quite strong. In fact, maybe stronger here because the concepts are more likely to be unique on one side than the other side. The functional coupling, still pretty weak, hopefully. We could write them in different languages. We wouldn't have a lot of shared code. So we're still looking at pretty strong operational coupling. What if we want to weaken it further? We could say, instead of making a query to go get the reference data, let's publish it via some kind of a message broker. Operationally now, we've got weak coupling. The reference data receiver can continue to run without the reference data system being alive at all. It can use whatever the last received message was. So we've succeeded there. The development coupling, still weak. We have now at least 2 and possibly 3 places where we can isolate the schema change. Semantic coupling, strong, maybe a little less so. We can do some translation in the message broker, although, part of me says, beware the enterprise spaghetti box. Don't try and put too much in there. Translation layers tend to grow over time, and so I might be hesitant to exercise that capability. The functional coupling now has strengthened because now we're using this messaging protocol. It's not as likely to be standardized. We may have some vendor dependencies. We may have some protocol versioning issues to deal with. So we have to make sure that everyone is using the same messaging tech on compatible versions, and the odds that we have to change both ends of this interface at the same time have gone up. Now, in each case, there was coupling. We can't really get away from it. It's necessary, it's inescapable. But some kinds of coupling are harder to deal with than others. So what I say is that the operational coupling, even though it's the most visible kind, is not the biggest inhibitor to making changes. The biggest inhibitor to making changes comes from the semantic coupling and the development coupling. Development coupling will tie your schedules together across different parts, different components, different products. And the semantic coupling will cause ripple effects that can eventually touch much of your enterprise. In fact, I have an example from a retailer that I worked with about semantic chains of coupling, where we underwent something that you might call concept leakage. We had this fairly typical retail enterprise architecture, a bunch of different pieces in there, starting with product information management, merchandising system called Retech, and this concept was created way back in the early days called a SKU, stock keeping unit. It was originally a number that was meant to track your inventory. So a SKU would have a count attached to it. Over time, people bundled more and more ideas into the SKU so that the SKU became the reference to your display attributes, pricing, shipping information, tied to reviews in some cases, and really a lot got attached to this idea of SKU, and so the notion of SKU propagated everywhere in the company. Eventually, it became so common that people just assumed SKU is inherent to e-commerce and merchandising. Well, this particular company then bought a hardware company, not like computer hardware, like hinges and screws and cabinet doors. They didn't use SKUs. They used combinations of attributes. So if you were to take the finishing screws that they sold and put in SKUs for every combination of thread density, material, finish, head type, length, and diameter, you'd have about 16 million SKUs that were all different representations of one screw. Just for the record, that would have meant 95% of everything in their database was different variations of a screw, and only 5% represented the entire rest of their catalog. They also went through another exercise where they were trying to create the idea of a price point as a way of managing prices across a large number of digital items all at once. So you take a music track that's at a particular bit rate, you want to now discount all of those, so you're selling them at 89 cents instead of 99 cents. Their old merchandising system would have required a manual update to every single SKU across, several hundred thousand. That's obviously tedious, so they created a notion of a price point. A SKU could have a price point, and if you change the price point, then that gets changed everywhere downstream. The problem is that they allowed that concept to leak out, and they sent the price point table along with the SKU table everywhere. So now every downstream system had to introduce this concept of the price point into their code, into their data. They had to receive a feed for it, and they had to add the logic to go look up the price point when a SKU had such a thing. It would have been possible to avoid that if the feed out from the system that knew about a price point just flattened the information and only passed on the official pricing, instead of requiring everyone to represent the same logic and the same rules. When I point it out this way, it seems fairly obvious that you would have preferred to not send the price point everywhere. But there are many, many things we do like this that we assume are part of doing business and part of the way that systems work, and we don't always see where decisions of the past have left us with a reality that includes a lot of this coupling. And when you have this kind of semantic coupling that stretches in long chains across the enterprise, I call it a semantic polymer. It's like, long chain hydrocarbons tied together, and you get something that's very stretchy and kind of hard to break apart. So I would like to leave some time for questions. I want to skip some of the less fascinating stuff and talk about what we can do with the slow animation, what we can do as a general practice to understand these. One of the key things is what I call rotating your perspective. So when you're looking at the operational structure of a system, you're looking at the components. This is the runtime structure. Sometimes a problem with the way the components are put together is best solved by rotating it 90 degrees and looking at the code modules that go into it. Not everything needs to be a service. It is still okay to write libraries that get linked into things. Those libraries have no operational coupling, right? When you're running with a library inside your application, you don't have to worry about differential availability from caller to supplier. Sometimes a problem in the modules can be solved with components. I think we're seeing this a lot with service mesh, where we're taking a problem of safety and availability and saying, instead of requiring every application developer to get it right every time, we're going to bake it into a component of the platform itself that we will always attach to the running application. I like to do Lisp stuff, so I try to tell people when you're looking at the data, think about solving data problems with code. When you're looking at code, think about solving code problems with data. If you're in a Lisp like me, you kind of look at that and you say, well, they're both the same thing. It's the same picture. More broadly, I would like us to use all the tools we have at our disposal to make the kinds of changes easy that we want to be easy. So we have the module structure, we have the component structure, we have the ability to extract similar interfaces and reduce the number of data types that we're passing around. The more you can do that, the more composable and recomposable your systems become, and that helps us navigate change better. So remember that coupling determines the degrees of freedom that you have. It enables some movements, but it inhibits others. It does connect effects that may be far distant, and sometimes those connections are not immediately visible or obvious from the runtime structure of your system. It comes in several kinds. Operational is obvious and visible. It's what we monitor for. Development coupling is more subtle. If we don't have declared types, if we don't have schemas on our interfaces, it may be harder to find these and you get breakage. Semantic coupling is the most insidious because it's not actually represented in any machine-readable form. I've yet to find a code scanner that can tell me when I've broken a semantic constraint. Functional coupling requires us to make coordinated changes, and we don't like coordinated changes. Interestingly to me, functional coupling often arises when you're using shared libraries to do the same thing in different areas of your system. To the extent where one CTO I knew said that two services that called each other could never be written in the same language. He actually required that they be different languages. It's a bit of a radical perspective, but an interesting one. So, in summary, we can reduce our functional coupling, we can reduce our development coupling by hiding decisions, isolating those semantics to the systems where they matter. We need to pick which degrees of freedom are really important. We don't want to have one part of our organization saying operational coupling is paramount, the other part saying semantic coupling is paramount, because what you'll get then is operational and semantic coupling across the united system. We've got a lot of structures available: dynamic, static, build time, and runtime. And in all cases, I prefer making things explicit in data and metadata than leaving it latent inside the code. So that is a whirlwind tour of what I've learned about uncoupling things. Thank you. I'm not sure where we landed on the time. Do we have time for questions?
Anyone have questions? Raise your hand.
All the way in the back.
I feel bad making him walk all this way. All I want to say is, I saw you flipping through all the architecture slides and I wanted to cry. So please tell me you have these slides posted somewhere where I can download them. They are posted somewhere. So I've given flavors of this talk at development conferences as well, where I emphasize more of the architecture. They were supposed to be hidden here. I'm going to blame Git for, well, because I can.
Yeah, they are posted.
Hi, thank you. Can you elaborate a little bit more about the semantic, and are there any tools or ways to figure them out?
So semantic coupling, fundamentally, it's representing the same concept in many different systems. And when I say concept, this may be reified as a table, an entity, an object, or even a data structure that represents, some similar construct. If you think about, if you're in an e-commerce company, you might have an idea like order. And you say, well, how many systems need to know about an order? Maybe a lot of systems need to know that an order exists, but they don't all need all the detail about the shipping address, the billing information, the line items, the quantities on the line items, and so on. And so you can say, I'm going to contain that concept of the full order in one place. And when I represent it in a fulfillment system, maybe what I have is not an order, but a shipment. By breaking that linkage, I'm now saying that the fulfillment system only needs to know what's going where, so that it can generate pick and pack orders and address labels and so on. But the notion of payment and whether it goes to a person or a company doesn't really matter to the fulfillment system. So by containing the idea of the complete order in one place, I gain more flexibility. I can now use that fulfillment system to send anything to anyone, anywhere. Similarly, I would take the order and extract just the payment information to go talk to the payment system, so that all it knows about is that I have an attempt to authorize payment for this amount of these categories of items for this payment method, form of payment. So the communication between them is really bridging these ideas. So order management is talking to payment in terms of payments. It's talking to fulfillment in terms of shipments. Only the order management needs to have the full picture. The more you decompose things that way, the more your systems become like their own little software as a service businesses. And that gives you a lot of flexibility to recompose them in interesting and novel and valuable ways. This is very much in line with the ideas of domain-driven design. So I would say there's a whole toolkit there in the DDD community for looking at how to break those down and create barriers so that your concepts don't leak all over the place. We had another question up here in the front.
Do you see Conway's law affecting coupling? What have your experiences been in terms of how you structure teams?
So yes, and thank you for asking that, because it's required that every speaker mention Conway's law. It's actually federal law now, and so I would be at risk if you hadn't asked that question. No, I do think Conway's law is at play here, and unfortunately, when we're architecting and designing a lot of our systems, we don't account for Conway's law. And so we sort of act like the master puppeteer that's creating this, elaborate orchestration across a bunch of different systems, which looks great on sequence diagrams, right? Like you get a sequence diagram this big and it looks like a railroad switching yard, and you're like, wow, that must be really valuable. But when you do that, you're making so many assumptions about the behavior of every piece of that system, and you're sort of like running a thread through all of them, and that thread then can't change. And so you run more threads for every use case and more threads for every use case, and now everything is stitched together into a tight web. I really prefer to sort of break it down and anthropomorphize each of the pieces of my system, and even toss around a tennis ball and say, all right, now I'm passing you this kind of a message. I want you to make a shipment to this address. You're like, yeah, I can do that. I know how to ship things. When you do that, you're sort of assuming that there's autonomy on each system to change, which aligns well with saying that there is a product team around that system that's able to make that change. I think architects sometimes fall victim to this sort of grandiosity where they want to be, the master orchestrators or the conductor of an orchestra. So I'm down on the term orchestrator for that very reason. Okay, we had a question up in the front. He's been very patient.
Yeah, hi.
Oh,
I really
you've got the mic.
appreciate this lecture. I thought it was very, very interesting. My question is, have you ever seen anybody be able to do this right across the multiple disciplines? I mean, I've been bit by this in development. I've seen it bite us in architecture. But holistically, coupling is not given the level of respect it deserves, I feel. And so I'm wondering, you had a couple of points of where to look, but have you ever seen anybody really do this right holistically?
Not the first time. And not even doing it right perpetually. Another sort of physics or astronomy analogy. There is a kind of gravitational attraction. Two systems that talk to each other sort of want to get closer and closer, and the interfaces become more specific. And that introduces greater and greater coupling. And so this will happen for a little while, and then you have to apply energy to separate things back apart again. I will say there are some architectural styles that seem to move toward that coupled state faster, and others that do it less quickly. I think event-driven systems move toward coupling slower than REST and request-response systems do. I'm not saying come at me or something on that. This is just my observation. Your mileage may vary.
So in the train example, coupling is actually pretty useful because you generally don't want your trains coming apart.
I'm sorry, could you speak louder?
So in the train example,
Yes.
generally coupling is a good thing, right? Like we don't want trains to be coming apart as they're going down the track.
Exactly.
Are there cases in architecture where having strong coupling is actually of benefit or useful in software, in systems architecture?
So I will say, if you keep it in limited domains, coupling can make it faster to get things done. And so if you're trying to do the first version of something, if you're trying to do a prototype or proof of concept, if you're trying to get something out really quickly, then the more closely it's coupled, the faster you're going to go. To the extreme case where you might prototype something just straight up as a little monolith, and then decouple it operationally when that becomes relevant, after you've learned, why you would want to do it. I will say, there are specialized domains, high-performance computing. You have a kind of a fixed topology. You're not changing it that often. You're aiming for maximum efficiency. So that's another one where I would worry about it a lot less. I don't happen to have worked in that myself, but that's kind of how that one goes.